So this video is going to focus on solving the skeletal structures practice problem worksheet. And again, this is going to focus on those neutral molecules. In the next video, we're going to have some where we see charges on some of the atoms. All right, so let's start with this first one. So the first set is to convert each of the following Lewis structures to a skeletal structure. And so to start, the first thing we want to do is count the number of carbons that we have. And so here we can see that we have 4 baseline carbons in the chain. And so we can draw out our carbon backbone. And so one thing I want to point out here is that we actually have a double bond in the chain. And one thing we notice is that the hydrogens are on opposite sides. And so when we draw out our carbon backbone, we want to make sure that we orient that double bond in the middle to be trans, where we have those hydrogens and the adjacent carbons on opposite sides of the double bond. And so we don't have to draw in any of the hydrogens so far because they're all bonded to carbon, so they're implied to be there. And so the last thing we have to add in is that last OH group, which is bonded to that terminal carbon over here. And so that should be our structure for that first one. And again, to double check, what we can do is just make sure that we have the same number of carbons, which is those 4 green ones in the middle. All right, for this next one, we can see that we have a 5-membered ring in the middle. And so we can start off by drawing out that 5-membered ring. And again, all of those hydrogens that are on the ring are implied. We don't have to draw them out. And the only thing left is to draw in that double bond to the oxygen right here. And so the final structure should look something like that. All right, this next one's a little bit more tricky. We can see that we have a lot more atoms here. So let's start off with highlighting our carbon backbone here. And so we can structure our chain around this longest middle portion of the ring here. And so we also, or not of the ring, of the chain. And so we also want to pay attention to these hydrogens next to the double bond, which we can see are on the same side of the double bond. And so this will be in the cis orientation for that middle chain. And so if we start off with these carbons right here, we can draw in that double bond. And so in comparison to the one right above it here, we can see that the double bond is going to have both groups facing the same direction. And then from here, we can just do the normal zigzag pattern. And we have 5 total carbons in the middle. And so from here, we can draw in that oxygen, then the carbon here, double bond to the oxygen with that hydrogen on the end. And last, we have to now add in this group and this group, which are both CH3 groups, to this carbon right here. So it can add in those 2 lines to show this extra carbon here and here. And then lastly, we just want to make sure we add in that OH on the other side of the molecule. And so we can add that in here. All right, so let's do this next one here. And so now this has a alkyne or triple bond between those 2 carbons on the end. And so one thing about alkynes is that we have to make sure that we draw them linear. We don't do the zigzag pattern for triple bond. And so what we can do, however, is a zigzag for the 4 carbons on the right. So I'll start off drawing those. And then here on this carbon right here, and I'll put a 1 here to show which carbon it corresponds to here. From here, we can draw in that triple bond. And again, instead of doing a zigzag, we're doing a linear pattern here. And one of the most common errors that I see students make with triple bonds is accidentally adding or removing a carbon. And so again, I really, something that I found is really helpful is to put a dot on every single carbon when you're first working with skeletal structures to make sure you're keeping track of the total number of carbons that you should have. Um, and so here we have a total of 6 carbons, which corresponds to those 6 highlighted greens in the middle. Last thing we want to do is add in those methyl groups that we have here and here. And so those come off from the second carbon from the end. So we can add in those 2 lines to show that they're there. All right. So for this next one, we want to convert the skeletal structures to the Lewis structure. So we're doing backwards of what we did before. And then we also want to determine the molecular formula of each structure. So to start off, what I'm going to do is highlight the longest chain of carbons and just draw that out linearly. And then we also have one more carbon right here, and so we can show that here. And so now the remaining part is just to add in hydrogens so that every single carbon has a total of 4 bonds. So we will have 3 on the end here, we'll have 2 here, and then this middle carbon right here is going to have 1 hydrogen here. And then we don't want to forget that carbon that's projecting off. So these carbon ones are pretty straightforward. You just have to make sure that we don't forget any of the carbons or hydrogens. And so from here, the chemical formula should be, we can count the total number of carbons that we have. So we have 5 carbons, and then total number of hydrogens that we have, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, let's move on to this next one. So from here, again, we want to count how many carbons we have, which is 4. And then an oxygen with a hydrogen. And then we want to make sure we include that double bond in the middle between those 2 middle carbons. And then from here, we just add in all the hydrogens. And again, we want to make sure that every single carbon has 4 hydrogens. If we take a look at these middle 2 carbons right here, we can see that the bond in the initial structure was trans. And so we want to make sure that the hydrogens we add are on the opposite sides of each other. So we're going to put 1 right here and 1 right here. And so by putting only 1 on each carbon, each of those blue carbons has a total of 4 bonds since it has a double bond. And then we can continue here. And then the last thing we want to do is add in those 2 lone pairs on the oxygen, since oxygen wants 2 lone pairs in its neutral state and 2 bonds. And similar to the previous one, to determine the molecular formula, we just calculate the total number of carbons we have, which is 4, total number of hydrogens, which would be 8, and then the total number of oxygens, which would be 1. Okay. This next one is looks a little bit funky because it's a ring structure. Rings are very, very common within organic chemistry, so that's why I wanted to make sure I included a couple of those within this video. So we can place a carbon at every point of the ring, and then I'm including those double bonds wherever they line up within the ring structure. And now we want to first take care of the hydrogens. And so each carbon within the ring has a total of 3 bonds. So for example, we can take a look at this blue one that I just highlighted. You can see that we have 1 bond right here and 2 right here. And so we need 1 more bond. So each of these carbons is going to have an extra hydrogen. And then the last thing we want to do is look at this nitrogen. And so we know that nitrogen wants to have a total of 3 bonds and 1 lone pair in its neutral state. And so it's missing that lone pair. And so we can draw that. And then to determine the formula, we would just do the same as before. We have 5 carbons. We have 5 hydrogens, and then we have one nitrogen. All right. So for this next one, we can see that we kind of have this internal structure right here. This is called an amide. It's a functional group that will be important later on. But for now, let's draw out the structure. So we have a carbon on the end right here. Then we have that nitrogen. Then we have this carbon right here that's double bonded to this oxygen. And then at the end, if we count the total number of carbons that we have down the middle, we should have 6 total. And then those last two are going to be bonded with a triple bond. Let me make this a little bit smaller so I can add in those hydrogens. All right, so we can right away add in that lone pair to the oxygen, and then that one lone pair to the nitrogen. So again, nitrogen prefers to have 3 bonds and then 1 lone pair. And then lastly, we can add in the hydrogens to each carbon. So the one on the end here is going to have 3 hydrogens. This middle carbon right here that I just highlighted in blue already has 4 bonds because it has the 2 to the side and then 2 to the oxygen. So we don't need to add in any hydrogens there. Then this next one is going to have 2. This one's going to have 2. And then this carbon right here also already has 4 bonds because it has a triple bond and then a single bond. So we don't add in any hydrogens there. But this last one right here is going to have 1 extra hydrogen because it only has 3 bonds so far. So we can add in 1 more hydrogen here. And so to determine the molecular formula, we'll do the same as before. We'll count the total number of carbons that we have, which is 6. Then we can count the total number of hydrogens, which is going to be 9. And then we have 1 nitrogen and 1 oxygen. All right, we can move on to this next one. So here we also kind of have this fused ring system where we have 2 rings that are fused together through that bond in the middle. And so similar to the other ring, we can start off with just drawing in those initial bonds here. And the tricky part with this one is making sure that you add in the right number of hydrogens. So here's the base structure here. And so now we have to go through and determine which carbons actually need an extra hydrogen. So these carbons right here and right here, all of those are going to need 1 hydrogen because they currently all have only 3 bonds. So let's add in hydrogens for each of those. And then let's take a closer look at the ones in the middle here. And so what we can see with those is that those already have 4 bonds. So if we zoom into this one right here, we can see that there's 2 bonds right here and 2 out. And so this carbon right here already has 4 bonds. And the same thing is true for that bottom one. And so for those 2 middle ones, we don't need to add in extra bonds or extra hydrogens because we already have those 4 bonds. And so lastly, for this one, let's count the total number of carbons that we have. We have 10 carbons, and then we have 8 hydrogens on the outside. All right, last one from this section. So again, let's put a dot on all the carbons and start drawing it out from the outside. And then what we'll notice is that we have have 2 oxygens, so we can add in those lone pairs to each one. And the last thing we now need to do is add in those hydrogens. And so we can take a look at this carbon right here. And similar to the one from above, we can also see that it already has 4 bonds. So we don't need to add in any extra hydrogens from what it currently has. This next one over only has 2 bonds so far, so we'll add in 2 hydrogens. And then next we want to take a look at these 2 carbons, which are part of this double bond. And so what we can see is that it's a cis bond where this group and this group are facing the same direction. And so when we add in the hydrogens, we also want to make sure that we add in hydrogens that face the same direction here. And then this terminal carbon right here is going to just have 3 normal hydrogens since it only has that one carbon-carbon bond currently. All right, and so to determine the molecular formula, we can just count out the number of carbons that we have, then oxygen or hydrogens and oxygens. All right, in this next section, what we want to do is for each of the following structures, we can draw in all the lone pairs of electrons and then draw in all the omitted hydrogens. So for this, let's start off with the oxygens and nitrogens. So here we know that oxygen wants 2 lone pairs and it already has 2 bonds. Nitrogen wants 3 bonds, so it already has 3, and I can highlight those here. So it has those 2 to the carbons and 1 to hydrogen. And so we want to add in 1 lone pair for this nitrogen here. And then unless we have something that's charged, the carbons almost never have lone pairs by themselves. So unless you see a negative charge on a carbon, you should never be placing lone pairs. All right, and so from here, the next part, what we want to do is draw in all the hydrogens. So similar to before, we're going to add in 1 to this ring structures because each of these carbons that I'm putting a dot over only has 3 bonds right now, so we need to add in 1 more. Next, we can take a look at this carbon down here and the ones that I'm highlighting in yellow right now. And so for both of these, we can see that the carbon already has 4 bonds because it has 1 down and then 1 to the side and then 2 up this way. And so we don't add in any hydrogens to either of these carbons because they already have those 4. Next, we can take a look at this carbon at the bottom down here. And this is also a very common mistake that I've seen people make where you accidentally forget that this one should actually have 3 hydrogens here since it's a carbon that's by itself. All right, next we can take a look at this highlighted carbon. And so here we can also see that this carbon already has 4 bonds. So there's nothing that we need to add to that carbon. So we can move on to the next one, which is right here. And so here we would want to add 2 carbons or 2 hydrogens to get to the full 4 bonds that this carbon would want. And then lastly, this terminal one is going to have 3. All right, let's move on to this next one here. So on the right over here, we can see that we have 2 types of triple bonds. And I intentionally included this example to illustrate the difference between how we show a internal versus a terminal triple bond. I'm just going to label this here. And the word for a triple bond is an alkyne. And then here we have a terminal triple bond, which is also, it's still an alkyne, it's just a terminal one. And so the way that we add in hydrogens is going to be slightly different to an internal one and a terminal one, even though they look pretty similar. So here what we can see is that on this left side, I drew a dot corresponding to every carbon that we have. And that this terminal one right here has only 1 bond right now. So we would want to add in 3 hydrogens to that carbon on the left side. The 2 in the middle that are highlighted in yellow, those already have 4 bonds because they have 3 between each other and then 1 to the neighboring carbons. So we don't add in any hydrogens to either of those carbons. However, when we get to these next carbons right here, we do have 2 hydrogens that we want to add into both of them, since both of those middle carbons only have 2 bonds currently. Then here, with the one that's double bonded to the oxygen, similar to the previous example, we already have 4 bonds, so we're not going to add any hydrogens to that one. But we do have to add in those lone pairs to both of these oxygens. And then lastly, let's take care of this terminal alkyne. So here, this carbon all the way to the right currently only has 3 bonds. So we're going to extend this out and draw in a hydrogen here. And then this one right next to it that I just drew an arrow to, that one does not need any hydrogens because it already has 4 bonds total. And so this should be our final structure here. All right, so for this next one, I'm going to go through it pretty quickly. Here on this last carbon right here, we have 2 hydrogens that we're going to add on because that carbon only has 2 bonds so far. This next one over has 3 bonds, so we'll add in 1 hydrogen. And same thing with the next one over, which also already has 3 bonds, 1 to the side and then 2 to the other side. So we can add in 1 hydrogen here. Same thing with this one. And then now that we get to the ring, let's take a look at this carbon right here that I highlighted in yellow. So this one right now has 3 total bonds. And so we have to make sure that we add in a hydrogen right here. Next, as we go around the ring, each carbon within the ring that doesn't have a separate group attached to it is going to have those 2 hydrogens. And then this one right here, similar to the one that we just talked about a bit ago, is also going to have an extra hydrogen right here because there's currently 3 bonds that I just highlighted that come off of it. Lastly, we want to take care of this part or this group like on the left side. And so one of those has an added hydrogen right here. And then these terminal ones on the outsides are each going to have 3. And so it's a really good example of why we want to use skeletal structures, because we can see that the skeletal structures are much more simple representations of these molecules. All right, let's take care of this last one now. So with this one, we have similar to the structure on the left, we have those 3 hydrogens that appear on the edges of each methyl group. This one in the middle is going to have 1 hydrogen. This one right here is going to have 2. This carbon right here is going to have 0 because it already has 4 bonds. And then with this nitrogen, the only thing we need to do is add in that lone pair because again, nitrogen wants to have 3 bonds and 1 lone pair. And with that, I think that wraps up this one.